is lesson 5.4, part 1. Today we're looking at can you use sum and difference identities to evaluate trigonometric functions and to solve trigonometric equations. Odd and even identities were covered already when we did our trig identities proofs. So you should already be familiar with these, but we're going to review them real quick. The even identities, which could be reflected over the y-axis, are sine of negative theta is equivalent to the opposite. Whoa, hold on 1 second. Sorry about that. The pen went a little crazy. All right, so we're looking at even and odd identities, and I believe this is actually odd, but sine of negative theta, or the opposite of an angle, is equal to the opposite of sine of theta. And this is also true for tangent. Tangent of the opposite of theta equals the opposite of tangent theta. I believe these are the odd identities. And then our even identity is cosine. This is different from the other two. Cosine of negative theta, or the opposite of an angle, is equivalent to the output of cosine of theta. And so cosine is the even because it functions like a parabola reflected over the y-axis when you're looking at the parent function. Sine and tangent, which are actually symmetric about the origin with rotation of 180 degrees. So those are actually the odd ones. Anyhow, those are the identities that we learned back in 5.1 and 5.2. We still need to know those. And now we're also going to look at the sum and difference identities. Sum and difference identities, we have cosine of alpha plus beta. Those are our angles in Greek letters. Equals cosine of alpha times cosine of beta. Minus sine of alpha times sine of beta. And I wanted to put next to it, so I'm going to try to slide over here. Nope, not going to work. I'll write it under, you'll have to write it next to. For the difference of angles for cosine, cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. So what's happening inside of the angles is the opposite side of what happens on the other side of the equation. And then we also have a rule for sum and differences of sine. Here's the sum for sine. Sine of alpha plus beta is going to be sine alpha cosine beta plus sine beta, or cosine alpha. I think your book does it cosine alpha sine beta, but that's fine, it's the same thing. And then for the difference, it's sine of alpha minus beta equals sine alpha cosine beta minus sine beta cosine alpha. That's for sum of two angles in sine and difference in two angles inside sine. So now we're also going to look at tangent. Tangent has two as well. I'm going to actually have to clear some of this to make space for it, but if you need to, pause it to finish writing it down. So here we go. For tangent, whoa, still having screen issues. Here we go. Tangent, we have tangent of alpha plus beta. And we also have the difference. That's not what I wanted. For the sum, it's going to be a large fraction, and you're going to add the sum of tangent alpha plus tangent beta in the numerator. you have to divide by 1 minus the product of those two. And similarly, for subtraction or difference of two angles, we're going to subtract the tangent of each individual angle on top in the numerator. And then in the denominator, we have 1 plus the product of the two. So here's example 1. And so what we're actually going to be doing with these angles is these are angles that are not on the unit circle, but we can actually use sum or differences with angles that are on the unit circle to calculate these values. And so when we can do that, we're going to use sum or differences so that we can, without a calculator, get the exact answers. So for our first one, cosine of 15. All right, so I'm probably going to use angles that are in quadrant 1. Maybe not, but most likely. So I look at that and go, how could I get 15? Well, there's a couple ways. I could do, I'm not going to add, I'm going to have to use differences. I could either do 45 minus 30 or 60 minus 45. I'm going to do 60 minus 45, and it's cosine. And the law of cosines, as you can see above, is the product of cosine with alpha and beta plus the product of sine with the product of the sines. So I have this, and give me 1 second. I just gotta. All right. So here we go. We have cosine of 60 is how we're going to treat this as cosine of 60 minus 45 degrees. So I look at my unit circle at where 60 and 45 are, and cosine is 1/2, and at 60, and we can see that sine is square roots of 3 over 2. So here's my 2 points. At 60 degrees, I have 1/2 comma square roots of 3 over 2, and at 45, I have square roots of 2 over 2, square roots of 2 over 2 for my cosine and sine values. So when I do this, what I'm going to do is I'm going to write it out using the rule. I have cosine of 60 times cosine of 45 plus sine of 60 times sine of 45. Now you could have also done this with 45 and 30. That would still give you the same thing in the end. I think that's how they do it in the book as well. But either one should give you the same answer. So cosine of 60 is 1/2. So this is 1/2 times square root of 2 over 2, which is square root of 2 over 4. And then for 60, it's square root of 3 over 2. Sine of 45 is square root of 2 over 2. So I have, so that's going to be square root of 6 over 4. So I have square root of 2 plus square root of 6 over 4. And that is, I can't reduce that without a calculator because they don't have the same value under the radical. So my final answer for this problem is square roots of 2 plus square roots of 6 over 4. And then I need a calculator to evaluate it further, but without a calculator, that's the best I can do using my unit circle, using just the unit circle. So all I did was figure out what angles would add or subtract, in this case, subtract to 15 degrees, write out the rule for the differences for cosines, which is the product of cosines, the product of sines, add them up. And then I actually evaluated each individual one on the unit circle, multiplied them, and tried to add them together as best I could. So now we're going to take a look at letter B. Sine of 5 pi over 12. Sine of 5 pi over 12 can actually, yikes. I'm going to have to think of things in terms of twelfths. Let's see. Pi over 6 would be 2 pi over 12. It may help to have a unit circle handy that you could change everything in terms of 12s if you would like to. We also have pi over 4, which would then be 3 pi over 4. And in fact, that's what I'm going to want. Hold on, 3 pi over 4 and 2 pi, which would 3 and 2 adds to 5. So there we go. So what I'm going to do is I'm actually going to use pi over 4, which is 3 pi over 12. And I'm going to use pi over 6, which is 2 2 pi over 12, and those two add up to 5 pi over 12. So that's why I'm going to use pi over 4 and pi over 6 as my answers. So I'm actually going to treat this, instead of sine of 5 pi over 12, it's going to be equivalent to sine of pi over 4 plus pi over 6. And the rule for the sum of sines is to add them, but do sine of the first times cosine of the second angle plus sine of the second times cosine of the first. So what I actually have here is sine of pi over 4 cosine of pi over 6, that product, plus sine of pi over 6 times sine of pi over 4. And so I need to know those points, those ordered pairs. Well, we already have the 45, the pi over 4 right here. The pi over 6 is going to be square root of 3 over 2, comma 1/2, right off of the unit circle. So it's important that you have one for practice, and we will be generating one to have available for us on assessments. So for sine of pi over 4, that's square root of 2 over 2, and that's going to be multiplied with the cosine of pi over 6, square root of 3 over 2. And then over here we have sine of pi over 6, which is 1/2, and sine of pi over 4, which is square root of 2 over 2, which again, at least in this case, ends up being the square root of 6 over 4 plus the square root of 2 over 4, which is square root of 6 plus square root of 2 over 4 for our final answer for this particular problem. Now they won't always end up adding to this, so just be aware of that. Cosine of 75 degrees. Well, that could actually be added with the 45 degree and the 30 degree angle. So again, these points right here that I have written down as pi over 4 and pi over 6, a 30 degree and 45 degree angle, since 30 plus 45 degrees equals 75 degrees. Again, I'm going to use law of cosines just like I did in letter A. So if you haven't already, you go ahead and pause the video and give that problem a try. All right, so when we do this, we have cosine of 40. I did 45 first, but cosine of 45 times cosine of 30, doesn't matter which order you have it, minus sine of 45 by sine of 30. So we just evaluate those. Cosine of 45 is square root of 2 over 2. Cosine of 30 is square root of 3 over 2. Sine of 45 is square root of 2 over 2. Sine of 30 is 1/2. Well, this time I'm going to have square roots of 6 over 4, and the other one's also over 4. And that's so square root of 6 minus square root of 2 over 4. Without a calculator, that's the most I can simplify it to. All right, see if you can figure out a way to figure out how to get 11 pi over 12, either using addition or subtraction. You may help to convert the things in quadrant 1, maybe even quadrant 2, in terms of twelfths. Now there are a number of ways to get to 11 pi over 12. One of the ways that you can get to 11 pi over 12 is to do 2 pi over 3 plus pi over 4. Because that would be 8 pi plus 3 pi each over 12. So if I treat this as pi over 4 and 2 pi over 3, one of them coming from quadrant 2, one of them coming from quadrant 1. There's a number of ways you could get there. You could also have done a subtractional. This is how I did it. That's what I'm going to do the tangent of. Because after all, this is 8 pi over 12 plus 3 pi over 12, which is 11 pi over 12. So I'm going to use the sum identity for tangent. And the sum identity for tangent is to add the things in the numerator and then do 1 minus the product of them in the denominator. So what I'm really going to do is tangent of 2 pi over 3 plus tangent of pi over 4 all over 1 minus the product of tangent of 2 pi over 3 times tangent pi over 4. So now I'm going to evaluate those and then try to simplify this large fraction that we have. tangent's not as convenient as sum and difference identities for sines and cosines. All right, so 2 pi over 3, that's going to be square root of 3 over 2 times negative 2 over 1, which is negative square root of 3. That's that one. And then tangent of pi over 4 is going to be 1. Well, that's convenient. And then in the denominator, I have to multiply those. So I have 1 minus negative square root of 3 times 1, which is negative square root of 3. So that becomes a plus. So now I have, and I'm going to do it over here on the side, so because I don't have much room left there, over 1 plus the square root of 3. Well, I can't leave it like that. I have to rationalize the denominator, but there's a plus sign, so I can't just multiply by square root of 3. I'm actually going to have to multiply the numerator and denominator, using our rules from Algebra 2, by 1 minus square root of 3. So on the bottom, that's going to give me 1 squared minus square root of 3 plus square root of 3. So that's why we did that. So that would go away. Minus 3. And 1 minus 3 is 2 in our denominator. In our numerator, it's going to give me negative square root of 3 times positive 3, or plus positive 3, then 1 plus 1 minus square root of 3. So it's actually going to be 4 minus 2 square roots of 3. From this, I can actually factor out a 2, giving me 2 minus square roots of 3 all over 2, which final answer for letter D is 2 minus the square root of 3. Except I made a mistake because 1 minus 3 is not 2, it's negative 2. Yeah, this was 1 minus 3. So it's actually negative 2. Since there was a negative on the bottom, I'd have this over negative 1, which I could just distribute the negative up here, making that negative and that positive. So that's actually my final answer. Example 2. An alternating current I in amperes is a certain circuit, can be found after t seconds using that equation, where 165 is a degree measurement. Rewrite the formula in terms of the sum of two angle measures. And then for part B, use the sine sum identity to find the exact current after 1 second. So, what else? Let's see, degrees, 165. I'm gonna need something from quadrant 2 at least. Let's look and see, maybe I'll use 120 and 45 will work. So we have I equals 3 times sine of 120 plus 45 degrees for both of those. So to find the exact current, we have to rewrite this though, because that's just me writing it out there. I have to rewrite the whole thing. So it's going to be 3 times the entire sum of sine of 120 cosine of 45 plus sine of 45 times cosine of 120. So we'll have to do 3 times whatever that sum is based on that formula. And so for 45, that's easy. It's square root of 2 over 2, whether it's sine or cosine. So this is square root of 2 over 2. This is square root of 2 over 2. Sine of 120 is square root of 3 over 2. Don't forget there's a 3 times out in front of the whole thing. And the cosine of that is negative 1/2. So this becomes square root of 6 over 4 minus square root of 2 over 4. And then we're going to multiply that whole thing by 3. So what I basically have is 3 times negative square root of 6 minus square root of 2 over 4. That's the exact value, I can get an approximate value by putting it in the calculator, but they didn't ask for approximate, they asked for exact. So that is the exact value, and that's as far as I can write it. Actually I could distribute that 3, so if I wanted to, I could do negative, it wasn't a negative 6, I don't know why I put negative. Those were both positive. So this would actually be 3 square roots of 6. If I'm distributing that, I can write my final answer as 3 square roots of 6 minus 3 square roots of 2 all over 4. Either one of those is okay. All right, last example for part 1. Finding the exact value of each trig expression. Oh, okay, so what they've done here is I'm looking at this and trying to recognize it as a sum or difference identity, and then work backwards to an angle that is on the unit circle. Because I see the minus up top, or in the numerator for tangent, I know that that is a difference identity for tangent. So this is, and the plus the product in the bottom. So it's tangent of 78 minus 18 is what this is. It's a difference identity, which is actually the tangent of 60 degrees. These should be the easiest problems. As long as you know your identities, you can identify them pretty quickly and just use your unit circle. So for this one, it's going to be square root of 3 over 2 times 1/2, which is just the square root of 3. For the next one, I have to remember the law of cosines. And with the law of cosines, the sine, when it's all written out, is opposite of what is actually happening to the angles. So this one is actually a difference of cosines. This is actually the cosine of 7 pi over 8 minus 5 pi over 24. Well, I'm going to have to get the same denominator, so I'm going to multiply that by 3. 21 pi over 8 minus 5 pi over 24, which is going to be 16 pi over, oh, this is 24 also, sorry, I changed the fraction. So that's going to be 16 pi over 24. 8 goes back into both of those, so that's equivalent to 2 pi over 3. So really, all of this is the same as the cosine of 2 pi over 3, which we can grab right off of our unit circle. 2 pi over 3 cosine's value is negative 1/2. So these two examples, and example 3, are identifying which identity you're using and using it to go to the other side to actually subtract or add the angles and evaluate it on the unit circle. Whereas the other problems that we did above were where we said, hey, that angle is not on the unit circle and I don't have a calculator, so I need to figure out what angles I could use on my unit circle to add to these values, and then use the identities to expand them like we did here, and evaluate each one and then simplify. So that is part 1 of 5.4. Can you use the sum and difference identities to evaluate trigonometric functions? That's the learning target that we've covered in part 1. In part 2, we will be continuing using those skills as we try to solve trigonometric equations. Have a great day.